Okay, so we move on with our next paper. So we have Clet Boudehenn, I hope that I pronounced that correctly, from the French Naval Academy, presenting his paper on a data extraction method for anomaly detection in naval system. Clet, welcome to Cyber Science 2020. You have 20 minutes for presentations and approximately 10 minutes for Q&A. So I look forward to hear what you have to present today.
Oh, okay. Okay, great. Oh, okay, that's good. Can you hear me well?
Yes, no problem.
Okay. Let's start the presentation. Okay. Thank you so much for the introduction. Thank you for attending my presentation. Hello and good afternoon. My name is Clet Boudehenn. I am a French PhD student from the French Naval Academy, and I work for the chair of cyber defense in naval systems. My thesis subject is about the improvement of anomaly detection in naval cybernetic naval systems. And today I'm going to present you my our article, which is entitled "A Data Extraction Method for Anomaly Detection in Naval Systems," that we done with Jean-Christophe Cexus on Abdel Boudra. Okay. Let's start by a little part of context. Today, the digital field has been widely deployed in the sea to respond to huge demand of economic exchanges. Oh, so not the good. Oh, due to the delay. Okay, that's good now. So today, the digital field has been widely deployed in the sea to respond to huge demand of economic changes. And now computer systems are everywhere on board, as well as in industry, power grids, power plants, on airports. This type of system have been deployed to provide an optimization of communication, navigation, and organization of the ship cargos. In that sense, modern mission ships have become a complex set of industrial and onboard systems with, for example, the development and the deployment of industrial control systems and SCADA systems. But even if this kind of system have been designed to have a long lifetime on board, because we talk about a lifetime about 15 and 20 years, so obviously it's pretty much difficult to change, upgrade, or fix this type of system. They have not been designed in terms of cybersecurity and present plenty of vulnerabilities that can compromise the proper functioning of the ship. And as a result, the number of cyber attacks on cyber physical systems has been increasing for several years. And now we estimate that 50,000 ships are so vulnerable to cyber attack. So new security challenges have emerged, and you have in the image, in the picture below, the cybernetic S7 300 and 400 and the input-output modules that present all of the vulnerabilities that I have talked previously. And this kind of system are the main targets because they represent a large open door to an attacker. And on the left or on the right of the slide, you have a short list of general cyber attacks which compromise the integrity of these systems. We have the recognition attack, an attack in which we can discover the network topology of the network, the open port, the IP address of this type of system, because these systems are connected into the intranet of the ship. We can make some authentication bypass. Most of the time, the password are the same, are the old default password. We can make some command injection and response. We can make some DOS, memory read on write logic, and also attack again PLC firmware. And this kind of vulnerability no need to be demonstrated with, for example, the advanced persistent threat and well-known Stuxnet virus in Iran in 2007, and also Black Energy and industrial attack in Ukraine in 2015, which target especially industrial control system like this that we can also find on board the ship. So to respond to that, the Naval system has been an increase of intrusion detection system deployment, but it's not sufficient at all to counter all these vulnerabilities. And the research community suffer with a huge lack of trained data to improve the cybersecurity on board. So one solution is to create the data by ourselves. So thanks to a cyber naval platform within the French Naval Academy and with the European project called Foresight, we try to simulate all the architecture of naval system on board. And here is the point. Modern machine ships are composed of a various of complex systems to ensure functional and operational requirements. And these pictures that you have here represent the architecture of the automatic layer of a naval system. And as you can see, there are two layers. The first one is the administrative network layer, which represents all the servers, the workstation, an application of the industrial control system that supervise the industrial processes with computers and human-machine interfaces. And the second one, just below, is the automatic layer, which includes plenty of physical components like industrial control system, distributed control system, programmable logic controller, and human-machine interfaces, and also input-output modules and boards that represent all of the sensors and actuators which generate the data. And everything of this architecture is connected together to ensure the navigation efficiently. All of these components allow to provide a different management system, such as in blue on the left, the propulsion management system, which ensure the main and auxiliary propulsion modes and also the navigation with the rudder helm, the stabilization, both thrusters, the propeller and shaft line. In red, you have the security management system, which manage the detection and fight against fire and floods, and the opening and closing doors, valves, and also the ventilation. In green, you have the power management system, which provides the high voltage power generation on board and provides sufficient power to, for example, the turbine, the batteries, etc. And finally, in yellow, on the right, you have the utilities management systems, which handle the fuel and oil consumption, the pneumatic and hydraulic distribution. All of this architecture is designed to respond of the lack of trained data, and it's totally simulated by a virtual environment. But we have also different physical components like the S7 300, 400, and the input-output modules that we've seen previously. And all of these components allow us to provide and to ensure to simulate the navigation. Concerning our contribution to improve the capabilities of anomaly detection algorithm, we have developed a data extraction strategy by focusing ourselves only on the propulsion management system. And down here you can see that we had some probes to gather all this cybernetic flow of the propulsion management system. In red, below you have the network probe. It's a TCP dump probe, thanks to a power mirroring connected to the switch and a Raspberry Pi to collect all the network traffic. And in blue, the blue one is to collect the physical flow from the sensor and actuator traffic in order to compare them with the network traffic. And all of the probes are synchronized in timestamp to highlight the correlation of anomalies and attack. In this picture, you can take a look of the input outputs of the proposed strategy, which represent the sensor, actuator, and network traffic from a normal operation. In fact, sensor and actuator managed by the input-output modules and the human-machine interfaces. It generates some basic quantities such as propeller speed and shaft line, fuel and oil consumption. And each quantities are simulated in function of another, allowing them to evolve over time. The data extraction was realized a few months ago, and we simulate the normal behavior over 5 minutes with a simulation of an acceleration and deceleration of the ship. In pink, the pink curve, you have the propeller speed with a scale from 0 to 100 to represent the propeller speed capacity of the ship. And there on the right, you have at the same time, you have the fuel and the oil consumption value that are decreasing due to the acceleration that you have at t plus 2 minutes. And below, you have the blue curves that represents the network traffic in terms of number of packets. An interesting fact is that the number of packets it's very determinist for this type of communication, because indeed this system uses the S7COM protocol to communicate, and it's almost the same number of packets that are sent. Because to be more precise, the number of packets is constant and correspond here to the net flow of 3 CPUs, 3 PLC, sending and receiving network traffic within the global architecture. Now let's add some complication. In this picture, you can take a look of the same outputs than previously, but this time with an attack which occurs during the data collection. This an attack that we talked just before, because it's the injection command attack with a specific role to do, because we can do here a PLC stop and start. Because this attack exploits a specific vulnerability of the equipment that allows an attacker to remotely control the on-off command of the PLC. Concretely, we just after do a nmap command to discover the network topology of this kind of systems, we can know everything, like the IP address, the use port, etc. And when we know the IP address, we can suddenly shut down the PLC and switch on it with a cycle of few seconds that we can change thanks to the Metasploit modules that we can use for this injection command. This is well illustrated by the plots depict on the figures, because you can see that the attack occurs 2 times and come after recognition. here you can see that this graphic show the evolution and of sensors and actuator and network traffic, and outline rapid changes. The blue curves represent the same than previously, but we have done only one CPU, and 2 CPU are still remaining up. But the attack had some consequences on the proper speed, particularly on the oil consumption, for example. And these graphics show the evolution of all of this. And this analysis, this graphic outline rapid changing that we can see here, and the analysis of such kind of changements required efficient tool to detect and highlight the discontinuities, such as derivative filter, for example. Now let's talk about the analysis. We propose a new detection strategy of these discontinuities based on the multi-resolution Teager-Kaiser energy operator, which is a quadratic and derivative filter. So here is the point. Detection of attack is performed by analyzing the local changes and discontinuities in data considered in time series. So the TKEO, the Teager-Kaiser energy operator, is a well-established tool to detect changes in time series or signals. And this operator has found many applications in signal processing and image analysis. And concurrently, the TKEO, the Teager-Kaiser operator, is an energy estimator from an oscillatory system point of view. You have on this slide a few equations about the Teager-Kaiser energy operator, and it offers excellent time resolution, because only 3, as you can see on the equation, only 3 samples are required for the energy computation at each instant. So it has a good adaptability to instantaneous changes in the signal. And due to its sensitivity to instantaneous changes in frequency dependent energy, the Teager-Kaiser energy operator is regarded as an efficient tool for detecting spike-like signals, and it's totally adapted for our kind of problem. So you can also the multi-resolution version of the TKEO that has been originally proposed to resolve 2 closely spaced stones. And for the last equation, where a large M value, which is the lag parameter, in fact, indicates a larger scale, since the involved sample are further away from each other, and the relevance between them decrease. The idea behind that is to use the multi-scale properties of the time series to identify anomalies by using the observation across the time scale. So if you take a look about of this spectra, you have the representation of the evolution of sensor, actuator, and network traffic with signal approach and analysis. And you have the same values than previously. We have the value, the speed, the proper speed, the fuel and oil consumption, for example. And we have also the network traffic in terms of number of packets with the PLC stop and start attack. We use so the multi-scale properties of the time series data to identify anomalies by using all of the observation across the time scales using the multi-resolution Teager-Kaiser energy operator. And time series are analyzed using 3 scales with M equal to 2, 3, and 4, as you can see on the second plot, and also here. And the PLC stop, the PLC stop and start attack are well identified for the three scales, showing the potential of the TKEO to detect this kind of anomaly. And this figure highlights that the more the scale increase, the better anomalies are evidenced by the TKEO. We just have to notice that all signatures of the time series, like, for example, transition, anomaly, attack, are converted in by the TKEO processing. And we still have to find the optimal number of scales, which remains an open problem for further analysis. As a conclusion, we describe here a new data extraction strategy to improve alerts management on board the ship, and show that sensor and actuator are pretty much relevant to improve cybersecurity on board, and particularly in naval systems. The proposed anomaly detection method based on the multi-resolution Teager-Kaiser energy operator helps to identify efficiently the injected anomalies from several scenarios, as shown in the most relevant scenarios with the PLC stop and start. Indeed, it's also shown the interests by exploiting the multi-scale structure of the time series. And concerning our future work, we're gonna go deeper into the analysis by extending the analysis to the entire architecture, because here, remember, we have only focused ourselves on the propulsion management system. Another future idea is to also generate a data set to benchmark anomaly detection strategies, and not only on the automatic layer that we have done here, but all over the global architecture, including, for example, the navigation layer with the enemy air traffic, the GPS, the IS, and the VAR. And finally, concerning the TKEO analysis, we think that a data-driven selection scale method will be helpful to perform the anomaly detection in an automatic way. Okay, so thanks so much for your attention and your interest.